Oh, there you guys. What's going on? Memes here. Yes, I know it's a wee bit late, but anybody that decides to join me on a Friday evening to discuss some total blasphemy, you're welcome here. But in the cosmological circumstances, that is. Listen, everyone's free to their own opinions. You do you, boo. But so what we're gonna do is Nolan. I mean, that makes sense to me. I could be wrong. Again, I apparently somebody had asked some qualifications. I haven't even responded yet. It's like my qualifications are I am a dude on the internet interested in this stuff. I I think a lot of folks might be able to identify that. Again, it's what am I gonna say? I'm a professionally trained physicist or mathematician. No, I am not. My only qualification might be I'm the luckiest son of a gun in the world. Um, it, again, that's a personal opinion, and I could be wrong because, well, that's science. Because we're often wrong about many things. If most ideas are wrong, then we should seek to be less wrong. Isn't that the whole paradigm of science? We seek to be less incorrect because then we go closer to truth. Shout out to Robert Lawrence Q. Um, all right, so where we left off. All right, so I think what was it on Wednesday we had gone over. We did this little structure here, and I'm trying to figure out why I have Deadpool drawn over there. I'd probably have to go back and actually watch the whole thing rather than editing out some clips. But I digress. So, what are we doing? So, what we are doing, this whole purpose of this stuff and things, is to basically maybe answer some questions. There's a lot of stuff I can put numbers and stuff on the board, and that's fantastic for me. I can scribble some stuff on a board. Human beings have been doing that for a while. But the question is, can we do something useful? Can we help explain the phenomena that we seem to be observing to the best of our science and measurements and technology and general understanding throughout the populace and stuff? Um, basically there are some questions. So we went through the whole, all right, if you had a primordial atom, a little bigger than like an electron or something, something ridiculously small, um, and, and then it were to go out, and then it would be kind of ridiculously big. Basically, the whole claim is most of the parameters of our lower U universe, because what's beyond there, I don't know, Zarbi dragons for all I know. Why do I need to say that? Well, big U universe, as far as I know, it encompasses all things. If I'm going to say, there's a limit of about 10 to the 34-ish meters for like a radius, we're putting a fine finitude on something that many people happen to say to be infinite. Now, why do people say it's infinite? Well, at least, again, my qualifications is I listened to a YouTube video of someone smarter than me. Okay. Basically, if you were to apply maximum extendability, what is that whole thing? All right. Basically, if you have a minimum thing, like a minimum length or radius, let's say, then by consequence, you would have a maximal radius. Okay. Now, if one of the big things that happens with, again, I'm not going to pretend that I know anything about quantum gravity or anything like that, but I'm just like, all right, if we run into that whole singularity issue, because it's all you do is the Einstein equation. Oh God, we get a singular point. We're trying to divide by zero. Give you a complex infinity, or at least according to my calculation on Wolfram Alpha, when I did one over nothing, you return to complex infinity because you're dividing by zero. Okay, because the claim is if you do that and you get below the Planck length, then we don't have a defined thing after that. Then at that point, it's like, all right, if we're going to assume there's going to be it's going to go down to an infinite point, like literally we're dividing by zero, then by consequence, the universe would go on forever. It's going to extend to infinity. Okay. A lot of folks seem to believe that, and that seems to be the current paradigm, and that's totally fine. It's Again, you do you, boo, whatever you find useful. Again, I am very biased on this because if you happen to come across somebody and they have some predictions and stuff, and it's like they're explaining, it's like that actually kind of makes sense to me. Okay, full disclosure, I did take like modern physics for like a week and a half in college or something like that. I was able to actually do some of the homework because as soon as it's like calculate the math energy of this particle going 0.9999999 times the speed of light, it's like, oh, I can get the answer. Why? It was interesting. So then I was willing to be like, all right, take the data, put it into the calculator, TI 83 plus, blah, blah, whatever it is. You put it out, you get some answers. I'm like, oh, it's basically the same thing as like a lot of finance stuff because I went to school for business and stuff. So it's like, oh, is that why like a lot of people that like study physics, if they're not able to get a job as like a professor or something, they just like go to Wall Street and make like a bunch of money? Because like a lot of the stuff, the underlying basically, if you're using similar math to figure out, okay, what's the discounted future of all potential dividends for this stock, you're gonna apply. Oh, actually, I guess we were using logs. Actually, now that I think about it, it's just I just looked for the formula. It's like, oh, okay, you're gonna take the average of this, and gonna be over X number of years. Bada boom, bada bing. You get that doesn't make sense to invest in this project, or should we just have our money set at standard, whatever, 7% market return or whatever? Again, I haven't been any of that stuff for a while, but actually, to be fair, I only really studied that in school. Other than that, I really just sold things. So yes, a sales dude. Yes. So obviously, be wary. Take what I say with an ocean full of salt. You can feel free to trust, but verify because everybody makes mistakes. It's like I don't know. Isn't that the definition of human? To be human is to err, and to be err leads to okay, I lost the analogy. All right, so let's get back to what we're actually supposed to be talking about today. All right, so we ended. Actually, let's just go into where we ended. Because we need a little inversion here. Because well, if we're going to be claiming inversions, we should probably live it, right? All right, so let's go back. So okay, where are we? Okay, so let's. That seems like a good a place as any to just bring it up. I don't know what I said after this. Let's see if I say. Ultimately, if we're just going to add in that, and again, the claim is if this is spinning here and we're starting from about the size of an electron, and we have all that hot, dense energy that maybe just converts into matter at some point because of baryogenesis, yada yada. Um, that's going to come out, and as soon as we add there, if it's in a super fluidic like state, because it's freaking going to be really, really hot, um, really, maybe it's going to start to condense into, I don't know, Avogadro's numbers of globular clusters, and then those globular clusters will come together to create galaxies and clusters of galaxies and super clusters, and then I know the Great Attractor, Laniakea, so much stuff. All these ginormous cosmological structures that are like, wow, that's really big. It's a really, hypothesis. We're gonna have to follow the evidence. We'll have to see where it goes. So this is probably a good place to stop right now, just because to commit more blasphemy, I think we should save that for maybe tomorrow or Friday. Yeah, because ultimately, where are we going to get to? I'm trying to follow. I don't know. This is the problem I have. I keep so many models in my head. I'm like, all right, what's the standard accepted thing? And again, do I know all this stuff? No. The general idea, maybe if there's a no-go somewhere, I'm like, all right, let's just take that, follow it as close as we can, and see if it matches. Why? I mean, if a lot of folks, if it happens to work, why would I just throw it away? Now, if you are going to propose something more out there, and again, I've already introduced a geometric object, but I think there's a lot of evidence and has a lot of very nice properties, but there's still a lot of work to do. But if we're going to do something beyond, okay, rather than matter and antimatter annihilating, what happens if we were to start with something simpler than just the quarks, protons, or neutrons? I'm like, is there something in common, some fundamental thing that we may have a way to explain more with less. So we'll end with this. I conjecture if we let there be light, and then we'll continue tomorrow. There we go. Blasphemy there. Let's continue our blasphemy. All right. We'll swap over to here. Did that actually work? Oh my God, it actually worked. All right. So I was able to actually multitask by playing something and then bring up the whole maximum extendability thing. Let's jump into this. From Bill Helper, aka Skydive Fit.
On Unbelievable loads of times. And every time you go on, you go, I should have said it that way. And when you're on one of these shows, it's it's not like you've got a prepared speech and you're riffing, and sometimes you don't say it exactly right.
That's right. So there's a feature that a space-time can have. It's a feature called maximal extendability. And roughly speaking, it's this feature that a space-time is as large as it can be. Another way to think about it is that it has no arbitrary boundaries. The only boundaries it's allowed to have are non-arbitrary boundaries. And now if you have a
can I just stop you for a
Yes.
sec, Dan? Does this imply, well, the universe could be infinitely big. So are we saying, well, it could be infinitely big, therefore it is infinitely big? Surely that doesn't seem right. What's really being said here?
So one way to think about
Okay, so I should actually probably comment because this is his interview and stuff, so I should put it in the link below. Okay, hopefully I remember to do that. But ultimately, he said it should be as big as it can be. I'm like, all right. So what's at least a logical train of thought we could take in order to apply some form of maximal extendability? So if I move my head, but all right. So what if we have, at least according to at least CODAD and stuff, we have a minimal unit of length that maybe it goes beyond that in some form, and I don't know. But we got a minimum unit of length here, the Planck length. Okay, 10 to the minus 35 meters. Very small number. If we did 1 over that, or technically what we should do is, for accuracy's sake, because if we did 1 over that, that will give us the inverse, which will be a big number, but it also has a unit attached to it. So what that does is that brings it to inverse meters, which is a weird thing. And that's not what we're looking for. So we need to be more accurate. I was like, commit more blasphemy. What you're gonna do? I know. What are we gonna do? We're gonna do meters squared. There's actually a silent 1 in here. It's 1 meter squared put over the Planck length will give us the inverse of it in the same dimension. Because this is a dimension of length, or excuse me, this is 2 dimensions of length. This 1 dimension of length. So 1 cancels out, that cancels out. That essentially becomes a literal, because this is also 1 here. So if you get something divided by 1, it ends up being itself. Cool. So basically, that's how we get about our 10 to the 34 meters, like 6.1 something times 10 to the 34 meters. All right. So we've got that. So what is our claim? Well, the claim is we've got a structure that's inverting upon itself. Somehow. Again, we're gonna still have to go through all I feel like it'd be like, okay, how do we get this so that we can solve for it given these particular parameterizations? It looks so simple and when you look into what your team knew and like the repeats and R's and stuff like that. What it is, it's like ultimately a lot of the framework. It's like, all right, you got 10 by 10 matrices. We'll just collapse it into some big letter or something like that. Yeah, that's a lot of work. But I think that was as a Schwarzschild solution was something like that was like 2 sine or 2 cosine. When you look at how he blocked it up and everything, and that's how they end up translating onto that 2 pi. No, excuse me, 2 gm divided by radius squared for the Schwarzschild solution for a non-rotating black hole, which then brings other questions. And it's like, okay, number one, we haven't observed. We observed the predicted effects of black holes. So we assume, like, well, it looks like a duck. If it's making sounds like a duck, 'cause, I mean, you can hear some of the gravitational waves, or at least those things being emitted from whatever the cosmic medium is around it. Maybe it's a duck, or in this case, a black hole, which I personally think should be titled mass holes. I'm also biased on that. Okay. So we've got this. Oh, let's finish. Few thoughts. That was the main point. Let's just see.
About this issue is that there's a theory that we use to think about possible spacetimes or possible universes. The theory is called general relativity. There's a central equation in that theory, the Einstein field equation. And when you're in say high school math class, and they give you these quadratic equations, and then you set the quadratic equation equal to 0, we'll solve for the roots of the equation, right? So those are the numbers that satisfy some condition that you've set up. Likewise, the
AX
Einstein field
something
equation
4A
has
divided by
solutions.
4AC
Each of
square
these
root
solutions, in fact,
AB,
there's infinitely
whatever.
many solutions. Each of these solutions is itself a possible spacetime.
Oh,
So when we talk about a spacetime model, one of the ways that we can think about them as the solutions to the Einstein field equation. Technically, if some viewers might know this, that the space of possible spacetimes is a little bit broader. We can think about spacetimes too that don't solve the Einstein field equation. But basically, we're just thinking about this
you're
this
going
zoo, this
to
collection
explain what's
of
going on.
mathematical models. And
Okay.
the question here is something like, so if I give you one of these models, I can imagine taking a particular model and then truncating it, making it smaller, and then
And then
then
focusing
someone
on
could say, well,
that.
why did you cut off those other parts of the model?
I need a pause just because I feel like I need to comment a little bit more. I need to see what he's getting to. Actually, that was my basic point. I would actually need to go through and actually, did I already comment on these? That's a great story. Okay, I think I was just doing some lighthearted, uplifting, trollish banter. Okay, so we can stop that for right now, and let's just go here instead. So he's talking about like solutions and roots. Okay, this is not the Einstein field equation. This is the stats hyperbolic partition equation. Why? You got a bunch of stuff here. Okay, you can believe whatever you want here. You can be like, why are you showing this? Okay, why am I showing this? Because at least this is a form of a simpler geometric structure, or at least arrangement of things. Personally, I think it's beautiful. Again, highly biased and all that, but I'm like, what is this thing? Well, it's an expression. It's 1 over x plus x cubed divided by 2 pi equals I to the I raised to the negative pi divided by 2. Minus a small number over here. Okay, what the heck is this? All right. Here's my analysis. Ready? We got a thing in the center. We've got the inverse of a thing over here. We've got basically a cubic, so kind of like a volumetric term over here. It's divided by a circle. We got like some rotation or something there. Okay. This is set equal to, what is this? If that hasn't written in different ways, this is the way that basically just my link is that. So I raised to the I. So all right, the imaginary number, what's that? It's the square root of -1. Okay, what happens when you raise it to itself? I'm like, all right. We think about that. That's like a rotation. All right, you get like a 90-degree rotation, but it's raised to I again. So it's another 90-degree rotation. I'm like, all right, that's cool because if you raise I to the 4th, then you go all the way back around. Or I think you get to 0. Yes, because you already have the first 90-degree rotation. Okay. And then this is raised to, and again, you could rewrite this if you want, but negative pi. So it's like you're twisting the other way, but it's a different twist. Instead of a 2 pi, a full rotation, only half a pi going in the other way. Well, that's like a 90-degree twist in the other way. How very interesting. And then we're subtracting this term out there. What the heck is this term? Let's we could do this instead. So let's subtract out, I think this will work. Planck mass divided by kilograms. Nah, it doesn't. Okay, long story short is if we do this, we go here, boom. 2.1764 times 10 to the minus 8. That's, well, we took a dimension. So the Planck mass, we calculate that from measurements and stuff like that. So the claim is that's a maximal unit of mass. Why? Because if you shove the Planck mass into the Planck volume, basically you're going to get the Planck density. And black holios. Oh God, that sounded wrong. Sorry, I grew up watching Beavis and Butthead. Cornhole. Okay, long story short. All right, 2.1764 times 10 to the minus 8. What was that number in here? I'll make one more. 2.1764, and then a whole bunch more numbers that's predicted by Thad's logarithmically based closed form for the Planck mass. Okay, times 10 to the negative 8. Okay. So I've got some geometric stuff going on, and basically we're subtracting out the magnitude of the Planck mass. Why? Because coincidentally, if you look off this term here, you're going to get some answers. And the gentleman over there, he was talking about the roots of equations for potential solutions to at least the Einstein equations and that particular concepts. In this, we're talking about something a little bit different. Why? Because this doesn't necessarily seem to be, well, I mean, the Planck mass, a lot of folks, at least ChatGPT loves to discuss the Planck mass being involved with quantum gravity. Oh my God. Did I break things? Run out of computation time? I have pro computation time. Oh my God, are they rationing computation because it's that? I probably need to sign in. Let's see. Oh wow. Hold on. Let's remove this. Let me get signed in real quick. Such a fail. Wow. You haven't played around in a while, have you? Yeah. Okay. So we got that. We got some more computation time. All right, let's go back. Let's try this again. All right. So, trying it again. It's gonna make me click on the thing. All right, try again. Wow. I don't know why this broke it. All right, let's add that term back in. Let's see if it makes it easier somehow. Okay, maybe it's just cached into my browser. I don't know. Okay, so long story short is when you subtract out the magnitude of the Planck mass from that, you're gonna get some numbers here. Don't worry, these numbers shouldn't mean a dang thing to you. But these are roots that will solve the equation. So we have two real solutions, aka they don't have complex components. So over here, we have two other solutions that when graphed out, happen to look like this thingy here. This is almost zero, but not quite. But these, as we can see, are in the imaginary plane. One is negative, one is positive, and then we have the second real solution out there. Cool. Why am I showing you any of this? Why is this of any consequence? Okay. So the claim of share the tab instead. The reason this is of consequence is we take this number here and we square it. We get this number here. Okay. Why should this be of any consequence? Well, if we click on this number, let's divide by the fine structure constant, which I think is in Wolfram. Okay. So essentially, here's the result. This number here happens to agree with the generally accepted number, or okay, maybe that some people there are experiments that disagree. You should be open about this, but this has an acceptance of let's see. So I got the first number, the second number, the third, fourth, fifth, sixth, seventh, eighth, ninth. So we have a little disagreement on the 10th significant digit there. Okay. Now, depending on whether you're using either, I think it was maybe, I think it was Harvard at one of the recent ones, basically right around here. Basically, here's where it disagrees. Let me get rid of this. They believe it's like, I think like a six something there, or 6.5 or something that has basically like a 2 there, that has basically about, I think, just over a 1 sigma agreement with the Berkeley Labs measurement from, I don't know, past 10 years, something like that. And again, could be wrong. You can also just adjust it by dividing the magnitude of the Planck mass by √2, and then it has there. It's literally right in the center, which is a little creepy. But again, it, if somebody's going to criticize you, why we deviated to the 10th significant digit. Now there might be good reasons for that. Okay, but basically they're talking about roots models, and wow, that was supposed to be a side tangent. I just rambled on. Okay, so let's get to what we're supposed to be talking about. Okay. So, at least as is generally understood for a lot of folks within the whole cosmogenesis thing and everything, it's like, all right, we start from a very hot, dense state. All right, a primordial atom, if you would. Okay, people have used that term. We're conjecturing it's about the size of an electron with 10 to the 61 kilograms of mass energy. Okay. Now, what I'm saying is, okay, you have that thing, let universe do its thing, let it take to its maximal size. All right, that's the claim. It's about a radius of about 10 to the 34 meters, aka about 100 million times larger than the observable universe. Frickin' ginormous, but you could at least, I've seen things where they've shown like or like $1 trillion in $100 bills. And you see it's absolutely ginormous, but you're like, all right, I could put like some magnitude. I've seen $100 bill at least once. I'm like, all right, that's a huge amount. Not that much. It's a lot less. So it'd be like seeing like $100 million could be in like a bank or something like that. It's like, all right, but we're saying already ginormous lower universe is already freaking enormous to us, like 10 to the 26 meters. Like if you look at something like the DESI results, the dark energy spectroscopic survey and stuff, they got some great 3D models where it's like you're zoom. Oh, actually, let's take a look at those. We got, I mean, if people are putting them out there, and it's a beautiful thing. It's like these are the things that should inspire people for science rather than just arguing totally not for their. It's that's the human condition thing. So let's see. As he survey, we'll bring up. Okay. Must click. All right. So you start seeing. Let's present. Share with class. All right. This is Mark. Let's take a look at this beautiful beam footage. Okay. Coincidentally, it kind of looks like a hyperbolic cone. Why? Well, because if we're taking it from our place on Earth, we're kind of, at least we believe, on the outer rim of the Milky Way galaxy. We kind of get a giant mass, like our own galaxy, blocking our immediate vantage point. So we're doing the best we can. But all right, so that's pretty cool. Okay, there's some. Oh, there's I think another. It's actually really good where they start like accelerating you through the cosmos. Okay, so the full dome. Okay, so here's from the actual. Okay. Oh no, they only have it at 7. Okay, we're only asking for the resolution of universe is all. So that's okay. So that's actually running there. Okay, and groovy. Where else are we at? I think they got another one that's kind of so, busy survey. Probably. Here we go. Oh my god. I haven't even been following them. What a terrible make-believe scientist I am. All right. Oh no. Listen, people find some value in this. Fantastic. Otherwise, I ain't the boss anybody. Well, maybe it's actually smarter. Let's actually just go to YouTube. Busy survey. Okay, all right. Of course, it's Berkeley. Berkeley Lab strikes again. Hold on, let me swap. Berkeley Lab strikes again. It always comes back to you. How dare you have great science? Believe is the thing. Okay, I think we're gonna line up. Oh, we got some pictures. I got some pictures. And we start the zone. Oh, that is cool. All right. I mean, that was totally worth it. So, um, yes. Where are we at here? All right. Let's go over here. Go here. All right. So, all right. What we were talking about? Oh, yes. So basically, there's apparently a problem between matter antimatter because a lot of believe it's during baryogenesis you're going to have approximately because if you're going to have your standard either Big Bang cosmology or you're going to have some nucleation event where all of a sudden matter and antimatter is going to pop out. And so if we're assuming fairly smooth stuff, it's probably going to be pretty even. But that antimatter is going to annihilate and it's going to cause all these things and stuff. So I'm like, so we're conjecturing matter and antimatter. Okay, that's cool. Is there another way that we could get to the observed matter and antimatter, so to speak? Or at least I mean, this is the human names that we've given to different attributes and properties that, I don't know, millions, I don't know, maybe billions of human beings have helped contribute to humanity getting to where it is nowadays. But it's like, hey, it is what it is. All right. So what happens if we were to start with, let's say, because I've kind of thought about this. I'm like, well, basically, if you're gonna have matter, and if you got to kind of have antimatter, then you kind of got to still solve that symmetry problem because it's like 10 billion times more matter than antimatter. It's like, I don't know. Is that a problem? Perhaps. Welcome, Charlie. All right, we're actually getting to the meat of the story. It's good timing. But I was thinking, I'm like, all right, well, that's kind of the easy one because I thought I'm like, neutrinos. I'm like, I mean, do we even really know what a neutrino is? To be fair, how much do we know about these other things? At least those other things we've kind of at least have some ability to do some manipulations on. Okay, so I'm like, all right, well, neutrons are basically everything what we need. Well, then we just had a whole bunch of neutrons and stuff. I mean, I don't know. I see at that point, is that going to cause an issue? Are we already going to be in a black hole? And then we just, what's going on there? So I'm like, well, even a neutron, if you're going to claim that, what if it's an anti-neutron? All right, is there an anti-neutron? Anti-neutron. Neutron. I know that word came out of my mouth. Is the antipower of a neutron possessing? Hold on. Anti-neutron is the right with the symbol. Okay. And only some properties of equal magnitude. Same as no net electric charge plus is because it's anti-quarks, blah, 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 blah. Okay. Okay, so apparently anti-neutrons are a thing, at least according to Wikipedia. And oh. Okay, so it's listing. Oh, it's listing code. Okay. So I thought about that. I'm like, all right, let's see how we could do this. Let's do particle physics. Now, perhaps there's some new particle. Perhaps there's some new thing out there that we have yet to discover. I'm sure that's the case. Now, is that required to solve what might be going on right now? So again, our friends at Wikipedia, feel free to trust but verify. Okay, so particle. Let's see. So standard model. Oh, okay. The standard model. Standard model. Here we go. All right. So this is what we require in order for the standard model of particle physics as we, oh God, it's a clickable chart, of course. All right. What we got here? We got the standard model of particle physics. Okay. The elementary particles, basically, we can only break them down so much. We can't break them down no more. Kind of, you're giving her all she's got. All right. So basically, we got our quarks here. We got our leptons over here, and these make our different hadronic components and our fermionic matter, more or less. And again, the broad categories, caveats, insert them here and there. All right. We got our bosons, which are our different force carriers and stuff. We've got the Higgs, which kind of seems to just do its Higgs thing and basically help, as far as we understand it, according to the model that we have, basically imbue different other particles with their mass. That's cool. Now, to be fair, actually, I don't know if the Higgs has an antiparticle. Is there an anti-Higgs? I mean, I'm just saying, if I do my little calculation, it's literally like, oh, and was it the Higgs mass divided by the Planck mass squared is equal to the magnitude of h bar? I'm like, well, unless I put magnitude symbols over there, I get a positive answer and a negative answer. So, I mean, full disclosure there. But that's not what we're here to talk about. What we're here to talk about is, coincidentally, at least before this moment, and I considered this, the only particle that really doesn't have its own antiparticle is the photon. Why? It is its own antiparticle. Why? We got a photon or whatever we consider a photon to be, a particle of light, so to speak, a waveform. It's going to go this way. If you have something going basically with the correct, basically they can cancel each other out. That's the thing. Basically, because if you have two equal frequencies, they're going to go there and boom. Wait, that doesn't make any sense. We need a, or it will hold on. So what happens when a photon meets a, wow. Okay. I'm finding flaws in my own logic. It's okay. That's fine. Look at these are the set rate of equations. This is equations, the standard model. Okay. I'm gonna have to put more caveats here because I'm considering my own. See, this is what happens when you don't have a full background in all these things. Where it's like, all right, it's gonna be okay. What happens when a photon meets a photon? Let's just do that. Me. Photon. I should probably just learn some Feynman diagrams. Photon meets photon of same frequency. There we go. I think as if now I'm like stimulated emission, where one photon triggers emission, another with the same properties they interact with photoelectro or Compton scattering. Okay. So I'm just gonna go back, and the photon is its own antiparticle. Again. All right. So let's actually get to the dang point rather than just bloviating along and showing how much I really don't know. Okay. So the claim is, at least when we have other particles and antiparticles and they come and they have the particular reaction, we consider that a maximal conversion rate because we're taking things that often have mass. We got one, it's matter, one, it's antimatter, it comes together, maximum conversion. Why? We get photons, often maybe some very highly energetic photons like gamma rays and stuff. So basically, we're getting a maximum conversion. So if the maximum conversion gives us light, and light might come in all its different frequencies, and it's going to have different effects based upon, well, basically, Einstein quantize it and everything. So it's like, all right, there's going to be certain things that can happen. Okay. So let's say if were to start with something, what could be the simplest base component? And again, we've already conjectured a particular. All right, you're going to have a toroidal structure, which happens to be the complement of the hyperbolic figure eight knot. So it's basically going to have this toroidal twist with a figure eight in it there. All right, so that's this little thing in the center here. There's a little torus with a figure eight configuration. The claim is once you have that minimal manifold of persistence, basically whatever configuration space you have, all the random waves there and everything might start to gravitate towards that, and all that energy or whatever it might be at that point is going to come in and it's going to invert out into the hypersphere of maximal volume. If you ask Google, that's not possible. But if you've done enough research and maybe talked to somebody that actually worked at CERN for a while, that was very knowledgeable, God rest John Williamson's soul. You look around and there is some literature on it. So does it need to be fully dissected and actually applied to what I'm claiming? Yes. Okay. But we're claiming a field configuration here. All right. So you've basically got that toroidal knot basically acting almost as like the 6 point for reality. I think more or less that ultimately is the claim that at least is coming out of my mouth right here. That knot is cinching together reality. We must remember, shout out to Kyle Hill, the figure eight knot is the best knot. Personal opinion, I think he said has never failed on one of his thumbnails. Hopefully that would, if there was anything to this, hopefully we would hope that would be the case. Now, okay, since there's a little toroidal structure, let me bring up the picture from hyperbolic figure eight, not complement. Okay, boom, boom. Let's do it here. All right.
Hi, my name is Henry Segerman. This is Figure Eight Not Complement.
Okay, so if you have this 3D object that's provided to us by Professor Henry Segerman et al., as you can see here,
You get when you subtract the knot from three-dimensional space.
you see there's that little twist in there. So these cutouts are just so you can see inside the thing. All right. So the claim is that's going to look like a little torus there. But as you can see, it's got this figure eight in the side. Kind of like if you had an apple, if a worm kind of ate its way through that, could eat around, and then come out the other side of the apple. So we take that wormhole. Oh my God. Save that one for later. Okay. So you've got this hole going through the torus. Now, since it's a figure eight, there's also a Mobius twist in there. So it's also undergoing some rotation. Okay. Cool memes. Cool story, bro. What is the point? Okay. So the point is if we take, we can do something like this. All right. So, all right. So if we take this object here, we plug it in there. This is our central point of balance in universe, so to speak. All right. And if we're starting around, let's say, the size of an electron, very, very small, there's going to be a lot of energy density there, right? Because if we let there be light, if we're going to use our base building block and we have a field configuration, that's a big ask. But if this field configuration does end up making sense, if it ends up holding water, and we've got this thingy here, no, this way, yes, this thingy in the center there. Okay. Now I believe at one point he says there's some rotation here. Let me get transcript. Row. Okay. 10. No, I might just be making it up. 3 and that point to choose. There is a projection. Reading the transcript because I could have sworn he said something like that. Constant radius, large radius, you're going through a radius is R3. Pattern in the grid, where's rectangular windows? Okay. Okay. So, well, we will make the claim anyway as, okay. So we'll go back there. All right. So we're back here. And it's like, all right, if we got this thingy in the center, it's undergoing some type of rotation. You get a very hot, dense energy state that's going to go outward in all the directions at c, speed of light. Okay. If number one, if there's a twist, one might claim, all right, maybe if it's a super fluidic like state, you're going to create little quantum vortices in that. Maybe that's how mass and stuff gets made. Okay. Maybe it does. Personally, I think that's how a lot of galaxies probably came to be, because coincidentally, if you take that 10 to the 61 mass number and just as a crazy idea divided by Avogadro's number, you get coincidentally very just about almost the exact mass of the typical globular cluster. I don't know. Do we use those things to make galaxies anymore? I don't know. But okay, how would we get to something like that? We've got a hot, dense state about the size of an electron. It's going to go out at sea till it hits its maximal radius, because we're going to try to maximally extend it from that minimum. Cool. All right. So if this thingy is rotating, and wait, if you could technically go up the vortex, let's just say maybe has a particular direction, because if you're going to spin stuff, you're going to create little vortices. And it's kind of like stuff going down a drain. It's like, all right, it goes down the drain, spins this way, and then maybe it's going to, if you look at the other way, it's going to spin out kind of the other way. Or maybe if it undergoes a little bit of a twist or something interesting might happen. So now, occasionally people, well, to be fair, I mean, if you're going to collide matter and antimatter and you have the correct amounts and everything, you're literally going to get light. Is matter light? Well, I mean, I don't know. I mean, well, at least according to E equals mc squared, energy equals mass times c squared. So you're squaring the speed of light times mass, and you give it, wait a second. Is that why light can't bend more than like 90 degrees or 45 degrees? Or yeah, it's like a 90. That's why the light cones go at 90 degrees, right? If it has to go at 90 degrees, it can't just stop. It's going to need to follow some geodesic. If you're to do something like that, I don't know, might it via some process or let's say morphism be able to square light in a hypothetically, let's say, a deformable way? And if you happen to do that, I should get matter as we know. If only there was a mechanism, we may be able to justify such a crazy idea. Now I'm just saying, I'm like, all right, let me do the little thought experiment. All right, if you got something like this thing could be spinning around. Do I know, is it the Planck frequency? Is it the speed of light? I don't know. It's going to add in some instability there because you're going to have some tension there. So maybe you're going to have different pockets. So maybe start spinning a little bit. Maybe you get that the seeds of the cosmos or stuff like that get there. But how do we get to the matter that matters? Okay. Hypothetically, if you have a very hot, dense energy state with, I believe the technical term is a butt ton of photons, let's say, or just you could argue about energy density or say you get a butt ton of photons. Let's say it happens to be going around and we had maybe a particular direction and stuff got sucked up there. So if you've got this light being sucked up by ultimately the field configuration that, at least in here, is being claimed that holds reality as we know it together. Yeah, I'm just saying that as a matter of factly, yes. Um, Again, you follow the science, we follow the arguments, we can see if we can explain more with less. Because at this point, if you give me a spherical Cal field configuration, again, we'll need to go through all of that. But if you grant us a field configuration, and this is the core of the field configuration, and it has the ability to suck up a buttload of photons. And if that were to be sucked up at a very intense rate, because as you can see, it's depending on how it's going to go there, you're going to get around to about 10 to the minus 18 meters, according to Thad's calculations. Coincidentally, that's about the potential conjectured radius of like a neutron or a proton, because they're very close. It's like, we don't actually know. Maybe we have the charge radius or something like that, and maybe even neutrons. Kind of, it's got the neutron kind of is. We know the neutron's radius to about 0 significant digits. We know the protons to we 1 or 2, I believe. It's not easy. It's very small. But so basically, the claim is if you were to have some form of a way to do baryogenesis to get the components within physics that we need, what if this object was basically rotating around, sucking up a whole bunch of light itself, and if it's traversing this thing, it's getting sucked in, it's getting condensed down to about 10 to the minus 18 meters, and it's going through this figure 8 style while twisting around Mobiusly and everything. Is this neutron decay cosmology? Kali, shout out to Kali Fisher. She's conjectured a bit of a different model using the trefoil and everything, but I'm just like, Lad wasn't looking for this at all, too. This just kind of came out from some calculations. And it's like, oh, what if we assume this? I'm not a geometer or a topologist, but I just look, I'm like, you've got a double cover of the minimal 3 manifold. First homology group is the integers. And again, I'm not a quantum mechanic. I'm more of a gamer. So within games, once you learn the general rules and the structure of the games, you realize there are certain attributes that might be useful. I think the integers is a very useful property because, well, from that, then you can do a lot more. You can do a lot of modern maths as we know it and everything. And then you also have the mimetic backing of the, I don't know, a very smart person said, God created the integers and then mathematicians took care of the rest, something like that. But basically, the claim is if we just start off with light, you run your universe going out to its maximum extendable size. As another smart person on Bill Harper's show, oh God, I had like this is why we can do the editing and the stuff after. So hey, K show, it's well, I mean, matter is energy too. Mechanisms, latency. Well, um, see, here's the thing. I think I did a thing on that before, Charlie, about latency because I was trying to see. I'm like, well, what happens if we had Planck frequency? We had Planck frequency, and like could we coherently have things together in a particular way? But tachyonic particles, I think that's if you're maybe in, I don't want to say inflationist. Oh my God, that sounds terrible. I've been watching some Mech Warrior lore. Oh, the Blakeists were like a big thing. I think we could learn a lot from the deep lore there. Just personal opinion. Uh, Tachyonic particle, that's assuming we are going faster than the speed of light. I mean, I don't think we need them. Again, that's a personal opinion. I could be totally wrong. Is that a dishwasher pipe? Dude, doesn't it look like an agitator in a dishwasher? That's where my mind went. I'm like, if you're gonna have something to agitate the where we live, our lower U universe, so to speak, it's like, well, why does things happen? 'Cause as soon as you put that, technically, those are just cutouts or a toroidal section right there. But ultimately, the claim is it's from Professor Henry Segman. This is the complement of the figure eight knot because the figure eight knot is, let's go here. Figure eight is something, basically these guys here. And basically, when you subtract that out, you end up subtract the knot. This is what you get left. Basically, a toroidal boundary, and yeah, a whole lot of really cool mathematical property. Oh yeah, it's also the this was the thing we did a little bit the other day because one of its characterizations. Let's have a link. 0, 0, 0, 0. An isolated critical point. Oh, what is that? Oh, it doesn't know. Basically, if you at least Google critical point, it's going to say basically a place that's in ill-defined. It's kind of like a singularity. So basically, it looks like if you really need a singularity, if this is literally characterized by at least, and again, probably wrong, within a four-dimensional coordinate system, it is literally characterized by a 0, 0, 0, 0 point. I don't know. Is that enough for you? We can just balance there. Does it make some of our problems go away? I personally think it might help if you have a minimum unit of length and you also have, I don't know, maybe a reason for why we don't need to divide by 0 and we just use our infinitesimal that we already have at least some calculations for, might help piece things together. Um, and then I'm extending that claim, saying, I'm like, all right, what happens if we were to conjecture that if we just start with light? We start with light, we have this 3D toroidal structure with that figure eight twisting in the center that happens to have a, almost like if a worm was eating through an apple, kind of like you'd have this wormhole that would go through, but it's twisting around with a Mobius twist and a figure eight structure there and sucking all this light into it, condensing it down to, according to Thad's calculation, about the charge radius of a neutron. And it's twisting around, twisting around. Are we effectively finding a smooth way to square light, my friends? That's what I'm conjecturing here. All right, we're basically out of time. Now, again, that's a crazy thing to say, and it's like I've said those words, and it's like, how does that even work? It's like, and then I made excuses. I'm like, all right, well, I don't have all that fancy. Flat has some fluid dynamics software that's really expensive. It's on an old laptop, so it's like, and those licenses are really expensive. So it's like, oh, I don't have the software. Boo hoo me. I'll wait for someone else to do some calculations. I did some calculations. I assume that if there was something to the words coming out of my mouth, and again, these are just rough calculations going through, you're going to need to do with all the other hydrodynamics and stuff like that, or whatever fluidic dynamics we see to use hydro and fluid very fluidly, interchangeably, which is interesting. But I did some calculations. Again, they're probably wrong. I still need to make my mistake, but even if it is a mistake, it's a thing. Occasionally you find something where you're like, I expect this to kind of be close, but this, yeah, it's not going to be the same. And it wasn't the same. The factor that popped out was very fascinating. So, neutron decay cosmology for the win? No, I guess we're going to have to see, my friends. The price of everything, I think, has gone up a lot. I had to, yeah, everything has gone up a lot. Yeah, I think I've noticed that too, but it is what it is. People are gonna, oh my god. All right. I swear I can learn to show. Why did I do that half? Okay. Because this is what happens when you go back and forth so much. All right. I need to get back into practice. All right. But that's all we got for it right now. I think next week we'll probably catch up with some potential neutron decay cosmology. I think Kali will like that. Yeah, we'll go through some of the other stuff and things. Other than that, y'all take care. Have a great weekend, and we'll catch you next time. Be safe, everybody. Peace out.